Hello everyone, welcome to the lecture. Today we are going to learn the stress in soil. The outline of this lecture includes the stress state and the Mohr circle, the self-weight stress in soil, the effective stress concept, and stress increase due to external loading. The stress in soil is of great importance to strength and deformation in soil mechanics. The stress states in soil mechanics is different from material mechanics, as shown in the figure opposite. The current pressure is positive for normal stress, and the counterclockwise shear is positive for shear stress. Based on the sign convention, the stress states can be presented in the sigma top plane, and the stress states in the soil elements can be represented as a circle, namely the Mohr circle. For the soil elements shown on the left side, the stress at plane BC and the plane AB refer to the stress states at point R and M in the Mohr circle, respectively. You can find the normal stress and the shear stress at any plane for given soil elements by using the pole method or 2θ method. For example, to obtain the stress state at plane EF by using 2θ method, EF plane can be obtained by rotating AB plane counterclockwise with angle of θ in the soil element, which corresponds to counterclockwise rotation of 2θ about center of the Mohr circle. That is from point M to point Q. Therefore, the normal stress and the shear stress at plane EF can be obtained from point Q in the Mohr circle. You can also get the stress at point Q using the pole method. In this method, you can draw a line parallel to plane EF from the pole, which is point P in the Mohr circle. The cross point between the line and the Mohr circle is the stress at the plane EF, which is point Q, and it is consistent with 2θ method. The self-weight stress refers to the stress applied on the soil at a given horizontal plane due to the weight of soil above it, which equals to the unit weight of soil times the depth for the homogeneous soil, as the expression in equation 1. For layered soil, the self-weight stress at any point can be obtained from the summation of self-weight stress above that point, as expressed in equation 2. Note that the effective unit weight should be used for the soil below the water level. Based on the equation, the stress distribution in soil can be obtained as shown in the figures. In soil mechanics, the effective stress concept is very important for strength and deformation related problems. The figure on the left side shows the column of saturated soil mass with no seepage in any direction. The total force θ times A can be divided into two parts as presented in equation 1. A portion is carried by water in the continuous walled space, U, times the area of water. The rest of the total stress is carried by the soil solid at the point of contact, PSV. Equation 2 will be obtained by dividing A at both sides. Assuming that the area of solid-to-solid contact AS is extremely small and can be neglected. Equation 3 will be derived, and the sigma prime is called effective stress, which equals the total stress minus the pore water pressure. The effective stress represents the average stress carried by the soil solid and its difference between the total stress and the pore water pressure. Deformation of soil is a function of effective stress, not total stress or pore water pressure. Deformation of soil is a function of effective stress, not total stress or pore water pressure. The effective stress concept applies only to normal stress and not to shear stress, as the pore water counts certain shear stresses, and therefore the soil solid must resist the shear forces. Now, let's find out the stress at point A, B, and C in saturated soil with upward seepage. For point A, the total stress equals H1 times gamma water, and the pore water pressure also equals H1 times gamma water, and hence leads to effective stress of 0 by using the total stress minus pore water pressure. For point B, we can also find the total stress, pore water pressure, and the effective stress using the effective stress concept. For point C, the total stress equals the weight of water plus the weight of soil above it, as expressed in equation 1. The pore water pressure can be obtained based on the method we learned from the one-dimensional seepage, which is presented in equation 2. Then the effect stress will be obtained in equation 3 by using the total stress minus the port pressure. Note that the hydraulic gradient I caused by the flow is h over h2. Equation 3 can be simplified by equation 4. The corresponding distribution of total stress, port pressure, and the effective stress are shown in the figure below. Similarly, we can find the stress distribution in a saturated soil with downward seepage. As water flows through soil, it exerts a frictional drag on the soil particles, resulting in a head loss. The frictional drag is called seepage force in soil mechanics, which is denoted by Gs as expressed in the equation below. Based on the analysis, a downward seepage increases the resultance of effective stress, and upward seepage decreases the resultance effective stress. Under upward seepage condition, if the hydraulic gradient is large enough, the effect stress may decrease it to 0. Under such a situation, soil stability is lost, which is referred to quick condition. The corresponding hydraulic gradient that leads to 0 effect stress is called critical hydraulic gradient, as expressed in equation 1, which varies from 0.9 to 1.1 for most soils. Based on the phase relationships, the critical hydraulic gradient can be expressed in equation 2. Since Gs is constant, the critical hydraulic gradient is solely a function of the wall ratio of the soil. Now, let's move to the problem of stress increase due to external load. Boussinesq solved the problem of stress produced at any point in a homogeneous, elastic, and isotropic medium as the result of point load applied on the surface of the infinite large half space. In Boussinesq's solution, the stress increase at point M due to the point load applied upon O can be expressed by equation 1, in which P is point load, V is the depth of point M, R is distance from point M to point O. In soil mechanics, the stress increase can be expressed as alpha times the point load P over Z squared, in which alpha is stress increment coefficient as indicated in equation 3. For the land loads of infinite length and has the intensity Q per unit length on the surface of the semi-infinite soil mass, the vertical stress at point A caused by the land load can be obtained from the integration of point load along the line as expressed in equation 1. The vertical stress increase at a point as a result of land load can be used to determine the vertical stress at a point caused by the strap load with the width of B as shown in the figure. To calculate the vertical stress increase, we need to substitute QdR for Q and X minus R for X as expressed in equation 1. The total increase in the vertical stress at point A caused by the interior strap load can be determined by the integration of equation 1, with limits of R from minus half of B to half of B, as illustrated in equation 2. Similarly, the expression for the vertical stress below the center of uniform loaded circular area can also be derived. Let the intensity of the pressure on the circular area of radius R be equal to Q, the total load on the elemental area, which is shaded in the figure, equals Q R dr d alpha. The vertical stress d theta at point A caused by load on the elementary area can be obtained from equation 1. The increase in the stress at point A caused by the interior loaded area can be found by integrating at equation 2, which is simplified to equation 3. Boussinesq's solution can also be used to calculate the vertical stress increase below a rectangular loaded area. We need to consider a small elemental area with dx dy of the rectangular with load q dx dy as equation 1. The increase in the stress d theta at point A caused by the load dq can be determined by using business solution as shown in equation 2. The increase in the stress delta theta at point A caused by the interior loaded area cannot be determined by integrating the preceding equation, as demonstrated in equation 3. There are also other types of internal loads, and the stress increase can be obtained by integrating the business solution. In solid mechanics, we normally use the stress increment coefficients in tables or figures to calculate the stress increase, which will not be further discussed. That's all for today's lecture. Thanks for listening.